Hello, good evening and welcome to this evening's webinar event. This is our last one in the series for VCE Specialist Mathematics, support for the revised study design. And I'm delighted to be able to introduce this evening Ray Rosen. Now, Ray is one of these blokes that I have often turned to when I've looked for assistance on particular programming ideas, clever little constructions in TI-Nspire. And I know I've often recounted the story when a student in my special maths class, when we were looking at one of the procedures, and she said, look, surely somebody could write a little notes application for this. And I said, yes, you're right. This is so algorithmic. And I reckon I know the exact bloke who would have done this. And it was Ray Rosen in Melbourne. So Ray, hoping you can hear us okay there.
Yes, everything's fine.
Perfect. And you know the story that I recount there was within, I think by the end of the day, I'd sent you an email and you'd written back and said, yes, this is exactly what you want. So the students were delighted. So thank you there. Now we've got Ray's screen on the webinar already, so it's already up and running on the webinar stage. I'm not going to waste any more of your time there, Ray, but I'll just say to participants, if you have any questions, please type them into the chat addressed to everyone. I will endeavour to respond, or sometimes I might have to interrupt Ray to draw his attention to the things that you're asking there. So take it away, Ray.
Okay, welcome everybody to tonight's webinar session. Now, this is really meant to be just on the VCA new bits which are in the new study design, which is the surface area of revolution. But the surface area is somewhat sort of related to the arc length, so I thought we'd also have a bit of arc length and surface area in here as well. All right, so hopefully you can see now the PowerPoint screen which I'm developing now. There's a lot of stuff here on PowerPoint. We've basically used integration in methods and in specialists to find areas between curves, volumes of revolutions when they're rotated either around the X or the Y axis. But in this session tonight, we're going to look at developing definite integrals, not only to find the length of a plane curve, which again has already been in the syllabus, but now to find the surface area of that volume of revolution. And we'll do it hopefully around both the X and the Y axes. All right, so for the length of a curve, if we just consider the curve, say y equals f of x, we want the length of that curve between A and B. If we blow up that little section there and look at that little bit of arc there, we've got a delta x and a delta y, and the arc length is the delta s. So we're sort of going to prove these formulas here. So suppose that we've got the continuous curve y equals f of x on the interval between A and B, the closed interval. Then that the arc length is made up of really infinitely many short little straight line segments. So let's just consider one typical point with coordinates p, xi minus 1, f of xi minus 1, and another point, the typical point q, which is xi, f of xi. So in our notation, we'll let delta x be xi minus 1 and delta y be f of xi minus f of xi minus 1. So then the length of that small slope, delta s, is the distance between the 2 points p and q. It's the square root of delta x squared plus delta y squared. All right, so let's sort of develop some formulas for the surface area now. There is a formula for a truncated cone, and hopefully we'll get some time to prove this formula later on. The formula for a truncated cone, delta S, now I'm using capital S for the surface area of the revolution, and a bit tricky, I'm using a lowercase s for the arc length. So the surface area or the disc or the frustrum or the truncated cone is pi f of xi plus f of xi minus 1 times delta S, or that arc length. Now, the idea to develop all this, I've sort of pinched from what happens when we wanted to find areas. When we want to find an area of a region, what do? We subdivide that region between A and B into sort of n equal strips, each of length h. So therefore we define x0 to be A, xn to be equal to B, and xi is equal to a plus ih. So it's the same sort of approach to subdividing an area into n equal strips. Sometimes we might use left and right rectangles, but it's the same sort of idea that I'm going to be using here to approximate, first of all, an approximation for the arc length and the surface area. So if we want to find the total arc length from A to B, then what we're going to do is sum over all such elements between x equals A and x equals B, take a large number of strips or little rectangles if it was an area. In other words, taking the limit as n approaches infinity or delta x goes to 0. So we have this formula S for the arc length. The limit of the sum of delta x squared plus delta y squared, we can just rearrange that. And when we take the limit of the sum, we get the definite integral. It's not really a true mathematical proof, but it's a nice little result there. Now, that sort of formula has been on the formula for the arc length, and we'll use it in a moment to find some examples by hand. But let's just have a look now how we can find the general result for the surface area. So for the surface area, we said that the formula was the limit as delta x approaches 0 for the sum of pi times f of xi plus f of xi minus 1, the square root of delta x squared plus delta y squared. The same thing, taking the limit as n approaches infinity or delta x approaches 0. That would mean that the f of xi and the f of xi minus 1 are sort of equal to each other. So we're going to get two of them. So we get 2 pi y delta s, and then the final line there, the total surface area is 2 pi, the integral between a and b of y times 1 plus dy dx squared dx. So it's a similar sort of thing for arc length. The only difference is we've got the 2 pi and the y there. Besides that, it's very much related. All right, so let's now go into a TI-Nspire page and let me look at an example that we're going to look at here. So suppose we're going to consider the curve y equals root x from the origin, x equals 0, to the point x equals 6. If we rotate that curve about the x-axis, it's going to form a volume. Now, we're not going to find the volume, we're not going to find the area, but what we do want to do is find the arc length and the surface area of that volume of revolution. All right, a nice little sort of application here is that we can sort of see we've got the curve y equals root x there, and this is the curve y equals root x rotated around the x-axis, forming the shape that we've got there, and we want to find the surface area of that shape. Nice little application there. All right, so first approximation for the arc length would be that blue line there. Now the blue line is just the line joining the origin to the end point, which is 6 root 6. And then again, I'll find that length. So let's have an approximation for that blue length there, which obviously is not the correct arc length. So what we need to do on the TI-Nspire, let's define our function f of x to be root x. Let's define the formula for the distance between the 2 points x1 and x2 to be the square root of f of x2 minus f of x1 all squared plus x2 minus x1 all squared. That's just the typical formula for the distance between 2 points x1 and x2. When I then try to work out d of 0.6, my calculator is going to give me an exact answer of root 42. When I press Control Enter, it gives me an approximate answer of 6.4807. So we're going to get some better and better approximations here. I'm also defining my surface area between the 2 points x1 and x2 to be pi times f of x2 plus f of x1 times the distance between the points x1 and x2. And then I'm working out SA. SA here will be the surface area. Again, the calculator gives me an exact answer of 6 pi root 7. My approximate answer there is 49.8712. All right, so that was just joining the 1.00 and the end point. Let's have another idea. Let's try to now join 2 points or 2 sub-intervals. Let's join the point 0, 3 and the point 3, 6. So we've got 2 sub-intervals now. This is obviously going to give me a better approximation to the arc length and to the surface area of those 2 bits when they're rotated around the x-axis. So this time, what I have to do is I have to work out d of 0, 3 plus d of 3, 6, and SA of 0, 3 plus SA 3 to 6. So it looks like obviously these answers are getting bigger and bigger. So that's with 2 sub-intervals. Let's try it with 3 sub-intervals. I've got my segment between 0 and 2, 2 to 4, and 4 to 6. And you can see that the blue lines now are getting closer to the correct value of the surface area and the arc length. So if I work out D02 plus D24 plus D46, again, I'm getting a slightly bigger answer, and the same thing for the total surface area. So let's try perhaps one more. Yep, let's go 4 now, 4 sub-intervals rather than 3. 4 sub-intervals means that the width is now, what, 1.5. And let's work out those and see what's happening here to the value of the surface area and the arc length. Again, it's increasing, but obviously it's not going to increase forever. It's going to approach a limit, which is the true value of the arc length and the surface area. So let me show you a nice little application now that I've developed. So considering all those applications that we did before, let me animate this one. So it enters 1, 2, 3, 4, 5, 6. You can see the value of the arc length and the surface area increasing. But I'll stop it at 20. We could go even more, but we can see that, as I said, it's increasing and it will approach a limiting value. All right, that's a nice little application. So I'll show you how I've developed that application. So basically what I've done to create that is to define f1 of x equals root x, because I'm graphing it. I've defined my distance x1, x2 to be the typical formula for the distance between 2 points. Now this is done on a notes page where things automatically get updated. If you haven't seen a notes page, I'll hopefully get time and do a worked example at the end, and I'll do it completely live. But this one I sort of pre-prepared. I've defined a to equal 0 and b to equal 6 and h to equal b minus a over n. And then I've got my formula for my arc length m, where m is the number of sub-intervals that I'm actually calculating. The CAS calculator has given the exact answer here. We could press Control Enter, as I said, to get an approximate answer. The surface area formula, remember it was f plus the value f of xi plus f of xk times the distance formula. And again, that is a nice little result, which will then generate all the results. Now, all of these values have been written in a spreadsheet page, and this is the nice little formula down the bottom that creates this application. The sequence command is a very powerful application, and it's a bit tricky to actually use, but comma h, x, x, comma a, comma n. What that's actually doing is in this, it's presenting the values of x increasing by h, starting at a and up to n times. So what this is doing, it's all related back to the value of n on this page. So if I increase, say, n to 6 and then go back to this page, you'll see that I've got 6 values here, and the values are 0, 1, 2, 3, 4, 5, 6. Whereas if I go to, say, n equals 2, then we've only got 2 strips there. The f value are the function values at the xv values. All right, so hopefully that's a nice little application there of showing how we can approximate and get better and better approximations to the arc length and the surface area of the investigation. All right, so let's go back to the PowerPoint slide now. Now, CAS, the TI-Nspire does have a built-in function to determine the arc length of the curve y equals f of x over the interval from a to b. So on a calculator page, just choose option 4 for the calculus, arc length option B, and complete the syntax using arc length of your function f of x, a, b. So we do have a formula for the arc length, but unfortunately we don't have a built-in intrinsic function for the surface area. They do have areas, and TI-Nspire doesn't actually have a volume either. So, you know, perhaps there's some additions we can think of for the people who develop it to put in a formula for the surface area and volume as well. Now, a lot of the questions you've probably seen for arc length are sort of contrived questions. I mean, find the definite integral to find the arc length of the curve x cubed plus 1 over 12x. And this is a typical exam 1 question. You've probably seen this exam 1 type question. It has appeared on past VCE exams in exam 1. But what I was sort of curious of is, can we develop some other curves for which we can find the definite integral? In other words, find the definite integral by hand. In other words, the integral can actually be done. Because a lot of these results, the integral that we get can't be performed by our standard methods. Some of them, in fact, CAS can't even solve, and we have to approximate the answers. So let's just look at a little worked example of this one, x cubed plus 1 over 12x. We have to work out the function dy dx, or the derivative. And the whole thing here is that 1 plus dy dx. Now, 1 plus dy dx gives me that. The whole point here is that we want this thing to end up being a perfect square. So we've got the 1 minus the half. Now, the half comes from the middle term there of 3x squared times 1 over 12x squared, and that has to cancel. The x squareds have to cancel, leaving me with 2 times 3 is 6 over 12, which is minus a half, because then it becomes 9x to the 4th plus a half. And that thing there is the perfect square. Now, as I said, these questions are all sort of contrived so that they work. So when we take the square root of 1 plus dy dx all squared, we just get 3x squared plus 1 over 12x squared. And we can write that as 1 over 12x to the negative 2. And as we said, that integral can be performed and can give us a nice answer by hand. Of course, we can use our CAS to get the answer with arc length. Now, any of these questions that can be done by hand, obviously also you could find the surface area of these types of questions as well. So what's the relationship between those sort of questions? So I thought this was a nice idea. Can we find some other curves for which we can find the arc length? In other words, which we can evaluate the definite integral by hand. So what's the relationship between m and c there in terms of n? Remembering, of course, we want this thing to sort of be the perfect square, which actually cancels out. All right, so a bit of algebra there. We'll let you sort of finish off this algebra. But remember, we want the middle term there in that expansion to contain no x's, to be the factor of what, minus a half. So when it adds to the 1, we just get 1 minus a half. So therefore, we just get 1 plus a half. So it's that middle term, 2 times n times x to the n minus 1 times m over c x to the power of m plus 1. That has to contain no x's. The x's have to cancel to leave that out. All right, so for that to be the case, the power of x is just x to the power of n minus m minus 2. That has to be equal to 0 because it has no x's. And therefore, m must equal n minus 2. And c must equal 4mn, or 4n n minus 2. In other words, we can now generate lots of curves for which we can find the arc length. So let me show you how we can do this. So if I define my function f of x to be x to the power of n plus 1 over 4n times n minus 2 times x to the n minus 2, then we've got one of them when n is equal to 3. And let me just animate that, and we'll see lots and lots and lots of curves for which we can find the definite integral of the arc length by hand. Now, it's interesting to note there that I've also included some negative values of n, -8, -7, -6, etc. But they're just the same as what some of the values are for positive values of n. So here's lots of questions that you can actually use in an exam 1 type situation to find the arc length by hand. All right, so there's that screen dump there as a Nspire page as well. And there you'll see all these questions there when n is equal to 3, when n is equal to 4, 5, 6, 7. So all of those can be done by hand to find the arc length and the surface area. It's a bit more complicated to find the surface area, but again, it can still be done. All right, so let's have a look at another example that we'll actually do. So let's find for the function f of x is root x, which is the one we did before. Let's set up a definite integral to find the arc length between 0 and 6. Now, this definite integral that we get for this one, we can't actually perform the integration. Or you could actually have a question where you could differentiate something and hence find the integral, but really the students at year 12 cannot find the definite integral for that one. However, the curve, when it's rotated about the x-axis, forms a volume. We can actually find the surface area of that curve by getting an answer of an integral, which can be done. So I'll show you quickly again the formulae for these. Y equals root x, or x to the power of a half. We've got dy dx, form 1 plus dy dx all squared, and then take the square root of 1 plus dy dx all squared, and evaluate that when x is between a is 0 and b is 6. So this is the example that we had in our investigation at the beginning. So the definite integral s between 0 and 6 of root 4x plus 1 over 2 root x dx. Now that integral, as I said, can't be done. CAS can do it and get an exact answer there of what a quarter log e 2 root 6 plus 5 plus 10 root 6. And it can be approximated to 6.6968. So as I said, CAS there, we'll see the screen dump for the CAS for that definite integral, and the arc length, it will actually give that correct result there. For the surface area, however, something sort of nice happens, as I said. So this time when we multiply by y, we're multiplying by y, which is equal to root x. So then the root x's cancel, and the definite integral for the surface area becomes pi between 0 and 6 of root 4x plus 1 dx. Now that integral can be done by standard means by students in the year 12 course, just by making what? A substitution. So if we make a substitution, u equal to 4x plus 1, du dx is 4. Don't forget to change our terminals from the old variable x to the new variable u. Then we can get a definite integral, pi on 4, u to the power of a half du. U to the half is integrable. We can integrate that to get u to the 3 on 2 and evaluate that between 25 and 1 and get a nice answer there of 62 pi on 3. So that one can be done by hand. So as we said, CAS does not have an intrinsic built-in function to find the surface area, but we can easily develop that on a notes page, or we could write a TI-Nspire program to do that. So in the TNS file that you will get for this, you will get the CAS program to find the surface area and arc length, but I suppose really just the notes page is sort of good enough here. So the notes page, define the function f1 of x is root x. Just for a bit of clarity there, I've defined df to be the derivative of the function f1 of x, and then the integral 2 pi between a and b of f1 of x square root of 1 plus d of f of x all squared gives me the exact answer that we've got. All right, so let's just go back to some sort of typical sort of applications here. Let's use this formula for the surface area to find the surface area of a cone. Now, what's the formula for the surface area of a cone? The formula for the surface area of a cone, we have to prove that it's pi r root h squared plus r squared, or pi rs, where s is the length of that line segment. All right, so this is fairly easy. If I want to rotate that line about the x-axis, what's the equation of that line? The equation of that line is just what y equals mx, where m is the gradient, and the gradient of that line is just m is equal to what, r over h. Now the nice thing here is that dy dx, or the gradient m is r over h, is just a constant. So when I perform all that in my formula for the formula for y, which is rx on h, times the square root of 1 plus dy dx all squared, that really is a constant. So forming the common denominator of h squared plus r squared, 2 pi r h, I'm only really integrating x between 0 and h. So a lot of nice things cancel out there. Let's evaluate that from x squared, which is h squared minus 0, and that gives us the result that we're requiring. All right, so that's the formula for the surface area of a cone. Now, the formula that we started off at the beginning to actually develop these was what, f of xi plus f of xi minus 1 times s. That's the formula for a truncated cone. Now, I was a bit unsure where this one came from at the start, so I'll actually prove this result for you as well. So here we've got a truncated cone. So what line am I actually rotating around the x-axis this time? The upper line there, well, what's the gradient of that line? The gradient of that line is what, r2 minus r1 over h. And it passes through the y-axis at y equals r1. So we've got its equation there. Y equals r2 minus r1 over h, x time plus r1. The gradient, dy dx, is just m, which is r2 minus r1 over h. And we can also see that in that triangle, if you think of the triangle there, L squared is equal to that distance, r2 minus r1 squared plus h squared. So once again, 1 plus dy dx all squared is just a constant. We still have the y there, so we have the only part where we've got an x is from the y. So that needs to be integrated. We need to integrate the x, so it becomes a half x squared. We need to integrate the r1, so it becomes r1x. We need just to be able to now substitute in x equals h and subtract off when x is equal to 0. And sure enough, with a little bit of algebra, we get the result that S, the total surface area for a truncated cone, is R1 plus R2 pi times L, which is the length of that curve there. And that, as I said, is the one that we used at the very beginning. So we've actually proved that result. All right, now remember when we sort of do areas with the x-axis, and then sometimes you can have the inverse function and find the area with the sort of y-axis by looking at the inverse function and looking where it intercepts with the y-axis. So we can do a similar sort of situation here. What we can do is, if we've got the curve now x equals g of y, and that's continuous between y going between C and D, then we can find the total length of the curve. This time, notice that it's the integral between the y values between C and D, but it's 1 plus dx dy all squared. Yes, there's always a typo. It should be dx dy all squared and g dash dy all squared. Alternatively, now, if we want to find the surface area, this one is correct. It's between the x-axis between A and B, or between the y-axis between C and D of y times 1 plus dx dy all squared. Okay. So now what we're going to do is we're going to come back. Remember the example we did at the beginning. The example we did at the beginning was what, y is equal to root x. So let's now consider the curve. Instead of y equals root x, let's consider the curve x equals y squared. Let's see if we can find the arc length of that one between y equals 0 and y equals root 6. Sure enough, the definite interval we get for that cannot be evaluated by hand, but we can evaluate it using CAS. And we can also find the surface area when that curve is rotated around the x-axis to find a surface area of that volume of revolution. Now, as you might expect, this is going to be the same, isn't it? We should get the same answers to what we got to the question before. So if x is equal to y squared, the x dy is 2y. Substitute in c and d as 0 and root 6. And sure enough, the integral there, 1 plus 4y squared dy between 0 and root 6, that is equal to the same answer that we got previously. And the arc length will also, that is the formula for the arc length. Now, you might be thinking, why does that work? Well, if I was to make the substitution in that definite integral as y equals root x, then really I'm going to get the integral that we had when we did it with the x-axis. Okay. For the formula now for the surface area, what happens now? 2 pi y, 1 plus dx dy between 0 and root 6. Again, this definite integral can be evaluated, right? Because if I now use a substitution, u equal to 1 plus 4y squared, du dy is 8y, again, change our terminals, and we get the same answer that we had before of 62 pi on 3. Again, think about why this is working, because if I let y equal to root x, then I'll get the same answer that we had before, or the same definite integral. All right, we can look at surface areas now around the y-axis, which effectively just means I'm swapping the x and y's, and we've got two formulas that we could have for this one. 2 pi between the x values of a and b of x times 1 plus dy dx all squared, or 2 pi between y equals c and y equals d of x times 1 plus dx dy all squared dy. So both of them will give the same result. All right, let's have a look now at what happens when we want to find arc length and surface area in parametric form. So if I've got my two parametric curves, x equals x of t and y equals y of t, then I want to find the length between the two t values of t1 and t2. Then it's given by that definite integral. And the total surface area is given by 2 pi y, the square root of dx dt squared plus dy dt squared. All right, so let's have a look at a nice example here. What is this curve? R of t. Now, I'm really going into vector equations here. The vector equation is cos cube ti plus sine cube tj. And although we're talking vector equations, we're talking speed. Speed is really related to the square root of the x squared dx dt plus dy dt all squared. So let's work through this example using the CAS. Let's try to find what's the name of this curve. Anybody know in the chat window? Type it in, Brian, see if someone can tell us. Find the speed, find the total length. When the curve is rotated around the x-axis, let's find the surface area, and let's try to perhaps eliminate the parameter t and get an implicit relationship and find the generalize and get the same results. All right, so I'll do this one live. So let's go into a new document now. And as I said before, I want to add a notes application here. So we're going to add a notes application. To get a maths box, we press Control N. So in my maths box, I'm going to type in define x1 of t equal to its cos of t all cubed. So you've got to sort of put them in. Similarly, another notes page, another maths box is opened in my notes page. I will define y1 of t equal to, this time it's sine of t all cubed. Okay. What were my values? Well, my values of t this time go between a, or t1 of 0, and b value is going to be equal to pi on 2. All right, so now really this is just one example. What was the name of this curve? Anyone know? It's called an asteroid. It's not an asteroid, little planets go around hitting other planets, or big rocks hitting planets and things like that. It's an asteroid. So let me just define now in another maths box my vector r of t. For this one, I want to get a matrix. A matrix is going to be what? A 2 by 1 matrix. Sorry, a 1 by 2 matrix. So we can get that from the template next to the book icon. So what am I going to type in there? x1 of t and y1 of t. Now, the reason I've called them x1 of t and y1 of t is because we can go into my graphs page and go to menu and go to graph entry edit, parametric, and my x1 and y1 are already there. Of course, it's not an appropriate viewing window, so let's go to a nice window to see what this curve looks like. We'll say -2 to 2, 1, -2 to 2, and 1. Yeah, just change the color. Let's change the color, make it look a bit prettier. Call it red. So that's our curve in a nice curve there, called an asteroid. Now, although that curve is a curve, you may have seen some applications where we can actually draw lots and lots of straight lines and actually generate that curve. Forgotten what that one's called. Anyway, so that's my position vector, r of t. In another maths box now, I'm going to define my velocity vector, v of t, to be the derivative of my position vector. Once again, just get the template for the first derivative, d by dt of r of t. Now, what's the speed? Question asks us to find the speed. Well, the speed is really, the speed at t is really equal to the magnitude, or the norm, the magnitude of a vector. We can type in, we can get it from the menus, from the vectors and things, but if you know what it is, norm is the way to go here. So it's the norm of v of t. So the calculator's put some absolute values in there, mod sine t, cos t. And there's an interesting questions on the Nspires there, is that because we're between 0 and pi on 2, that would be equal to what, half of sine of 2t, and therefore we don't really need the absolute value signs between 0 and pi on 2. Okay, so if we think back to the curve, at this point 1, that's 0, 0. This is the point where t equals pi on 2, t equals pi, 3 pi on 2, and 2 pi's back to that point there. So what is the total length of the curve in a maths box? The length of the curve, well, it's going to be 4 times the definite integral. So this time I want the definite integral between a and b of the speed. Okay. That's because I didn't define my speed to be equal to the norm of t. I think it should be the norm of, between the sign to equal to, shouldn't it there? Yes, little typo. So the length is equal to 6. That's the total length of the curve between 0 and b, but it's 4 times because we've got 4 little bits. But what's the surface area of that total curve there? Do we want 4 times it now? No, think across, go back to here. We're really rotating this curve about the x-axis. So if we're integrating between 0 and pi on 2, then we really only want twice it. So this time it's 2 times the definite integral between A and B of y. So it's also, we need 2 times pi. Nice little shortcut there. You can just type in pi of y1 of t dt. No, we still have to multiply that times the speed. And hopefully this will give me the correct answer. Yes, 12 pi on 5. So this is a nice little application which you can then save. And if you save this, really all you have to do is just change any of these functions above this line for your x1, y1, your a's and your b's, using a bit of symmetry, of course, to find the total length and the total surface area for any question involving parametric curves. So as I said, speed, position vectors, velocity vectors, arc length, surface area are all ultimately sort of related. All right, so let's just go back to the PowerPoint to have a look at some other nice, here's the question done for us again by hand with the same screen dumps that we had before. All right, I didn't do it parametrically. We're running out of a bit of time, but if x is equal to sine cubed t, y is equal to cos cubed t, sine of t is x to the power of 1/3, cos of t is y to the power of 1/3. We eliminate the parameter sine squared plus cos squared is equal to 1, then that gives me x to the 2/3 plus y to the 2/3 is equal to 1. I could use implicit differentiation by hand. We could do this on the CAS and try to simplify 1 plus dy dx all squared using the fact that x to the 2/3 plus y to the 2/3 is equal to 1. And we can actually work it out and get the same answer there. Now, for the surface area, 4 pi between 0 and 1, 1 minus x to the 2/3 to the power of 3 on 2, which is y, times the arc length, or the integral for the arc length is x to the minus 1/3. You wouldn't think that that integral is actually going to be coming out to 12 pi on 5, but it actually does. So there's the screen dumps to show that those two values are the same. All right, just want to conclude with 1 or 2 more worked examples. Just to know some sort of good little party tricks here. You can prove the area of a circle is pi r squared. We can prove the circumference of a circle is 2 pi r. And in fact, the derivative of the area is in fact the circumference. Yeah, it's a bit strange about that one. What about the volume of a sphere? We know the volume of a sphere of radius r is what, 4/3 pi r cubed. What's the surface area? Surface area of a sphere is 4 pi r squared. It's also the derivative as well, isn't it? Okay, well, let's just prove those results as a nice little application and finish off with hopefully one more worked example. So I've got the solution for this one up here. I'll work through one more example here. X squared plus y squared is r squared. Y being the top half of the circle is the square root of r squared minus x squared. And using implicit differentiation, once again, we'll get 2x plus 2y dy dx equals 0, or dy dx is equal to minus x on y. We'll get the total formula for the total surface area between negative r and r of y times the square root of 1 plus dy dx all squared. X squared plus y squared is r squared. The y squared is just square root of y squared in the denominator is y, cancels out. Sure enough, we get 4 pi r squared. So yeah, it's a nice little example to show your students. Or it could be, we could really develop a SAC on all of this sort of stuff. You know, finding the area of a circle, finding the arc length, things like that. So the parametric forms for the circle is x equals r cos t, y equals r sin t. Again, I prefer the notation x dot as dx dt. I don't really like x dash because the dash normally refers to derivative with respect to x. Now, we know that the value of r is positive. Once again, we could just adapt the program or the notes page that I had before to work all this out. And it's very easy to prove that the total surface area is 4 pi r squared. And once again, we could do that parametrically, or just alternatively using the functional form. We get the integral there of r over root r squared minus x squared, which you can see is the r sine of x over r, and we get the same result for the total circumference of a circle of radius r. All right, so just to finish off, I'll just hopefully got a bit more time. When we're rotating the curve around the y-axis now, we're going to have the formula. We've got two formulas, but the one I'll be using is x times the square root of 1 plus dx dy all squared dy between the y values of c and d. All right, so a nice little sort of question I was thinking up when I was in bed looking at the lampshade here. We've got a nice little lampshade there. So my lampshade has got a base radius of 20. The top radii is 10. The total height of that lampshade was 30 above the ground, so the total length is just 20. The total height of the lampshade is 20, and we're sort of modeling that edge of the lampshade as a function between 10 and 20 of a sort of a hyperbola. F of x is a over x plus k. And presuming, of course, the dimensions are in centimeters, let's try to find the total surface area of that lampshade. All right, so I'll do this again on a calculator page. I'll just start up a new calculator page here. So what do we know? This is not a notes page. This is just a normal calculator page. I'm not going to sketch the graph, so I'll just define my function. Oh, it's a over x. All right. It looks like I'm using the a's and the b's from before. So perhaps it's a better idea that I do insert a new problem so I don't have any conflict of interest between the a's and before. So now we'll define f of x equal to a over x plus k. Now, we know that that curve passed through the point what x equals 20, y equals 10, and x equals 10, y equals 30. In other words, f of 20 is equal to what? F of 20 was equal to 10, and f of 10 is equal to 30. So really, we have to solve those two equations for the values of a and k. So I can just go up and get them. You know, my students always say, oh, you're typing so quick. Well, I'm not actually typing, I'm just grabbing and pasting. And we're solving that for what? My values of a and k. So sure enough, I've got my values of a and k. Well, now we really have to redefine my function f of x, and given that the values of a and k are now defined. So now I've said given that a is equal to 400 and k is equal to minus 10. All right, now remember, we have to get this one round the other way. So I'm going to have to find the inverse function because I'm going around the x-axis. Sorry, I'm going around the y-axis. So let's resolve this f of x equals y for x. So I've got now x in terms of y. So let me define my function. I can call it x1 now of y. We don't have any issues with before. And again, I'll just press up arrow and delete my two equal signs there. All right, so what's my total surface area now? My total surface area is going to be 2 times pi times my definite integral between this one. We're not doing, as I said, on the notes page, we're doing it by hand. It's between 0 and 30. I've already got the 2 pi, so it's x1 of y times, it's going to be what? The square root of 1 plus the derivative, so I need my template for d by dy of x1 of y We needed to square that. So let's put in a bracket around there and squared. And all of this is a function of y. So we're integrating with respect to y. CAS comes out with a sort of very nasty integral, which it can't actually evaluate. Sure enough, we'll press Control Enter, and there's our answer. Now, as I said before, let's try to do this same answer, but this time do it in terms of x's. So if I'm going between x, so in the integral above there, y went between 10 and 30. What is x going between? X is going between 10 and 20. What's my integral now? Instead of x in terms of y, it's x times the square root of 1 plus, what do I want here? Here I want not the derivative with respect to y, but the derivative with respect to x of my function that I've defined as f of x. And sure enough, what do you think this one's going to be? The same answer. So we've verified that little formula there, that when I've got 1 plus dy dx all squared, or we can do it with respect to y. All right, I think I've gone a bit over, but I hope that's been some nice little worked examples for some arc lengths and some surface area questions that we could actually work through by hand. And yeah, so there's the lampshade one there. All right, so have we got any questions, Brian? There are lots of other worked examples I could actually work through there, but yeah, I've got lots of other worked examples. I'm just trying to find my last slide to say, yep. Yeah, I probably went a little too fast in some of these, I know, but hopefully you can watch this recording in your own time and have a look at the worked examples and try to sort of perhaps figure them out before you sort of have a think about how I've gone through some of these fairly quickly. But as I said, I had quite a few more worked examples, but when we've got that notes page for the parametric one, we can do it any way we sort of want, just by changing those functions x1 and y1. And it also, as I said, arc length is related to the surface area, and it's also related to the position vectors, velocity vectors, and finding the speed. So I think that's sort of a nice thing here about the specialist maths course, whereas all these topics are sort of interrelated. So any other comments or questions, Brian? I didn't hear you. Yep.
Yeah. Well, my comments there are, yeah, certainly you're going to have people calling for an encore there, mate, when you gave us the preview to the other examples. I can see in the chat people expressing their thank you for the ones that you have showed us there. Comments that I've got, I think the whole thing very clear and approachable for students. And I'd just like to point out that even though this particular webinar series is directed mainly at teachers, you can always grab these and use them with your students. I know I've done that before too, and as I mentioned earlier, Ray, I've used your materials with my special maths class. We do have, if you want to look on the TI website, there's all of the recordings, and soon it will be this one as well, for the study design revisions, this one being the last in the specialist mathematics series. And there's also separately webinars accessible via the TI webpage, or also on the Texas Instruments Australia YouTube channel. And that there's a great resource there for students. I really think, Ray, and I know you're the expert on CAS, but I really like also your step-by-step, line-by-line reveal of what you were referring to as by hand solutions. And I think, as you suggested, for teachers and students to be going back and reviewing this with the video and also with the PowerPoint that you'll share, to go back and analyse that slowly and see, yes, I understand how each of these steps works. We do need to bear in mind that as wonderful as the CAS system is, it's our students also have a calculator-free exam, and of course, for their actual understanding, they need to do the hard work, hard slog calculus, along with also what they can see side by side with the CAS. So that I thought was very inclusive. You got your parametric graphing, uses of different, implicit differentiation. We were doing your substitutions. You had your changing the terminals. You're swinging us about the x-axis and the y-axis. I loved it. And it's not hard to see why you're the expert on this, Ray, and why a lot of our teachers and students will have met you before at the revision lectures, and of course also know you through your textbooks. So I will once again thank our presenter this evening, Mr. Ray Rosen, one of our national T-Cube trainers, coming to us from Melbourne. Our session tonight on the arc length and surface area of solids of revolutions in the Specialist Mathematics series for VCE. Thank you for your comments that you've been typing into the chat. We hope that you find your way to the recording of this and also the support documents that Ray will be sharing, and wish you all an enjoyable evening. All the best.
Good night. Thank you. Bye.